Okay, welcome. So we're doing continuing on with solving rational functions or simplifying rational functions. So here we have a rational function. It's a degree 2 polynomial divided by a degree 1 polynomial. 7x squared plus 56x over x plus 8. What do we know about simplifying these? Well, in essence, we're trying to figure out if part of the division can be executed, right? Maybe in its entirety, but if part of it can be executed. Because if it can, then we can actually look at an equivalent thing, an equivalent expression that takes on the same values. But we know there's this certain nuance to start with, which is to say that if we're saying something is an equivalent expression, if we're establishing an equal sign, then it needs to be exactly identical in every input-output pair. And that includes, for example, if the initial equivalent function has a domain issue, which this does. So for example, we find out very quickly that we can't divide by 0, and therefore in this case, f cannot take in -8. If it tries to, it will try to divide by 0, which will break. Excuse me. So we want to, cannot be -8, of course. We want to hold on to that idea in case we simplify. It doesn't always happen in the simplification that we eliminate this type of thing, but in case we simplify and this x plus 8 kind of gets to be divided out, we still want to understand that x equal -8 is a problem for us. So let's see. F of x then equals, let's do some factoring. Well, it looks like 7x can come out. Okay, 56 is divisible by 7, and there's certainly an x in common. So we're undoing a distribution, or we're factoring out into a form that is pre-distribution. And we do that because it is only in the multiplicative sense that we can think about executing some divisions, right? So we need a multiplication in the top to really understand what factors we're able to say are in common and therefore divide to 1. And you can see it, hopefully. That's going to be equal to 1. And so this is 7x, where x cannot be -8. So you might think about what that means, okay? We know, for example, this line will be something relatively steep, like this. But at -8, x equal -8, let's call that right there, there is a singular point hole, right? When x is -8, it feels like this f of x should be -56, but it is not. It is a gap. It is a little hole there. So it's a domain issue, and it is expressed graphically by that hole. If the hole wasn't there, then we would say it's exactly 7x. And when -8 is plugged in for x, the output is -56, but it's not. Remember that f ultimately is this thing. Everything about that thing needs to be identical. And when x is -8, that thing is not -56. It does not exist. Therefore, we represent that with that hole there. Okay, good first example. On to a second. Let's take a look here at a new problem. You'll notice that today I'm using some function notation, so I'm actually writing this f of x business. And we remember from our first lesson that when you use this type of equal sign, this one is an assignment equal sign. We are stating from a blank space that f is this rational function. And notice that it bears no relationship to this f. We are kind of in a reset. We're back to a blank set. F, G, H, none of them have anything assigned to them until in the specific context and problem we're told maybe what they are, or we say what they are for ourselves. In this case, when we're told what f is, that's useful. And now it directs us, it kind of guides us to say, okay, what in this case, of all the functions we could be thinking about, we're going to think about this one, and we'll call this one f for right now, so that we can understand it in shorthand. And so I think a good idea when you're doing these problems is to attempt to factor top and bottom. Because then ultimately, when you're trying to simplify here, you're trying to see whether or not part of the factoring matches top and bottom and can divide to 1. So let's do this factoring. I think I'm looking at x minus 4, x plus 3 on top. I think that should work. And how about on bottom here? Well, what are my options here? I'm seeing 18 and 2. I'm seeing 6 and 6. I'm seeing 12 and 3. And I'm seeing 9 and 4. And 9 and 4 add to 13, so I think those are good options. X minus 4, x minus 9. Noting that we covered this in previous videos, so if you haven't watched them, go back and look, where this is the easier cases of factoring of a quadratic, where the leading term, the thing connected to the x squared, is 1. Just 1x squared, so it's a bit easier to factor. But ultimately, don't hesitate to check your answers, where just multiply these factored forms of numerator and denominator back out and make sure that you get back up to the top. If you don't, it's likely you've made an oversight in the factoring process. So what does this tell us? Well, there's more information than just the fact that x minus 4 seems to divide out. We also want to take this factored time to recognize that x cannot be 4 or negative 9, positive 9. That those x value inputs won't work. So this is stated in a lot of ways. It's stated as saying maybe x equal 4 and x equal 9 are not in the domain of f, meaning they do not give an output. There's no output. F of 4, f of 9 does not exist, another way of stating it. Very, very, very important to handle the nuance of the difference between having no output and having the output of 0, right? So often we might think about 0 as like nothing or none. That's perfectly appropriate, but we want to distinguish none from no output, right? And 0 is an output. 0 is an output, but no output is not an output. It's literally not included. So that's the type of thing we're dealing with here, where we can't divide by 0, and therefore if we put 4 or 9 in, it's not that we get 0 out of f, we get absolutely nothing out. In other words, if you try to plug it into your calculator, there's an error. Now, let's finish it out. That goes to 1. And so f of x is x plus 3 over x minus 9, where x cannot be 4 or 9. And you can bet on in a multiple choice scenario, this type of thing being actually the determining thing to finding the correct answer. In other words, if this were, say, in a multiple choice, if this were choice B, it's very likely, as somebody who's written tests and taken plenty of them, that this could be option C. And that the subtle difference of is x equal 4 in the domain or not? And this is where, if you're looking at the final answer here, or the final form of the equivalent function, prior to thinking about domain, you will probably get it wrong. You will look at this, and even if you know about domain, you'll say, oh, the only issue here is dividing by 0, and that only happens when x is 9. But what you're ignoring is that this is a simplified form of this initial f that we're given. This is ultimately the f that we're talking about, and that has two domain problems despite a simplification. What is actually mathematically happening here, which is peculiar and difficult to deal with in a lot of ways, is that when you plug in 4 to f, the initial f, the top is 0 and the bottom is 0. It's 0 over 0. And so it feels like, oh, 0 over 0, something divided by itself should just be 1. And therefore, like, we don't have any problem. But that's in fact not the case. 0 divided by 0 is such a unique and bizarre case that it too implodes in many cases, and therefore here, as an example, x cannot be 4 either. All right, let's do another one. Oscillate between harder and easier ones. So first step, this is a unique issue, right? In the sense that what we really want to do as the first thing is to establish the domain issues in order to make sure that we don't kind of erase them and not see them anymore. And there are likely going to be domain issues very frequently. And if you just factor and divide, you might not ever really account for them. But this is the counterbalance issue, which is you want to know when f breaks. So when the denominator is 0, what x's make that happen. But in order to know that, you actually often factor, right? And so there's this relationship here of it's a risk almost. 6x comes out. X minus 2 left. 5x x minus 3. Okay. And so what do we get here? Well, we get f of x equals 6 times x minus 2 over 5 times x minus 3. In other words, these x's divide to 1. But we should recognize that in the same type of way, if we only look at this final simplified version and say, oh, hey, x can't be 3, we will probably get this question wrong, even in a multiple choice situation. Of course, in a short answer, it is wrong, so that would be wrong. But even in a multiple choice situation, we will probably get it wrong because this is probably going to be a choice. In order to kind of question whether or not you recognize where the issue happens. And so it happens up here. So we've established from the simplified version that x cannot be 3, but we've established from the factored version that x cannot be 3 and x cannot be 0. So what we really want to say is that there is a difference in spirit between the top two here and the bottom version. The top two, yes, it is an equivalent form, but all we have done is factor. We haven't actually simplified. All we've done is factor. And so if we pause after we've factored, that's the time to hit the pause button and say, okay, not only am I going to look for things that actually divide out in order to simplify, but I'm also going to look right now at all of the domain issues prior to simplifying. And that includes x equals 0. So x cannot be 0 either. And that would be the correct answer. That would be the correct answer. Okay. All right, let's do a couple more here. Let's see here. How's this? G of x equal to okay, sit with it, read it. We're talking about a new function g of x equal to x cubed minus 6x squared minus 40x. I have no idea why the screen is moving. I wasn't even touching anything. Divided by x squared minus 7x minus 30. So right away, we're in a different situation than some that we've been looking at, where here, in this rational function, the top polynomial is actually degree 3. Now we'll see that this is kind of, as we know, there's a layering on of complication usually as we're learning math. And this is one more layering on where it's like, okay, we've dealt with quadratic factoring, and that is pretty difficult, and we have a bunch of tools. So what about maybe, does that set of tools, like finding things in common and or doing kind of an anti-distribution, does that set of tools help us with maybe some x cubes? And yes, it does. The other side of it is that I know that there may be domain issues. And so the general first step to simplifying a rational function is to factor. And so I'm going to do it in multiple steps here. I think the first thing is that I want to say that there is an x in common between all three of the terms in the numerator. I also want to say that I'm looking at x minus 10 on the bottom times x plus 3. So what's interesting here is, and this is perfectly fine, you don't have to do all of the factorings at once. You can piecemeal them out and rewrite and do another equal sign and take it one step more factored until you're done. I've done 2 factorings. I took the x out at the top and I actually factored the quadratic in the bottom. Now, because the quadratic is factored in the bottom, I know that x cannot be 10 or negative 3. And so I want to make sure to bring that information around every time I'm talking about this g of x. Now, back to the idea of factoring like in a piecemeal sense or in multiple smaller subfactorings. Here I'm looking at a semi-factored form here, but nothing seems to divide out. But I'm not done. And so now we need to see, maybe there is still a simplification to be had if this x squared minus 6x minus 40 also factors. And it looks like it does, as x minus 10x plus 4. All right, those, I've been doing it this way, saying those divide to 1. So g of x equals x plus 4 over x plus 3, where x does not equal 10 or negative 3. That could be the right answer if they leave it in factored form. Sometimes, when we're thinking about the overall umbrella of simplifying, you may actually be called upon to go back from factored form to more general form. So in my experience, that line would not be the answer. Actually, this line would be the answer that we're really looking for when we're talking about the most simplified. You might ask yourself why, and then what was the point? Well, remember that factoring what's done in order to see if we could execute a division. In this case, we could. X minus 10 divided by x minus 10 goes to 1, and therefore we've simplified in a pretty significant way both the numerator and the denominator. However, the numerator as x times x plus 4 remains kind of an unsimplified form. Remember, we dealt with this very early on. If we were just looking at a new function, x times x plus 4, and we're asked to simplify it, our step is to execute the distribution. We would say, oh, it's x squared plus 4x, and that is simplified version of this. And I think it's compelling. Yes, it looks a little bit simpler in some ways, right? We don't quite get this information about like x equal negative 4 being somewhat interesting and making h 0, but it is also simplified in the sense that like we just have to plug in x in the relevant spots and do some addition and a little bit of multiplication. In the factored, this one, we also have to remember to distribute correctly and things like that. So in other words, distribution, so doing a distributed multiplication simplifies a polynomial. Okay, so actually executing a distributed multiplication simplifies a polynomial. But in a rational function, which is the division between two polynomials, it is very frequently that you want to anti-distribute, you want to factor so that you can maybe execute a division as we did with g of x right here. And in order, after you've executed the division, however, you've kind of gotten all of the juice out of the squeeze as far as factoring goes. You're simplified via factoring. But factored form is not the simplest form. It just gives you access to a tool of simplification, which is doing this division of like terms top and bottom. And therefore, we very frequently then, in order to get the right answer, which would be this one, we need to redistribute that numerator. So remember, the goal of simplification is in essence to find the least complicated, fewest distributions form that is equivalent to the original. And so that's what we have here, not the line above, where we still have this distribution in the top. So we want to cancel things, we want to divide or add to 0, divide to 1 or add to 0, or whatever the case might be for combining like terms. But we also want to distribute. Okay, let's do one more. Oops. Alrighty. Trying to simplify this thing. What's interesting is moving forward, even if simplifying isn't the initial task, it can sometimes be a good intermediate use of your time in order to make the other question maybe you're trying to answer about this question, this function, simpler. That's the virtue of simplifying. So let's see. Let me try to factor the top. I'm looking at x minus 7, x plus 1. Let me try to factor the bottom. I think that I'm looking at x minus 7, 2x plus 1. Now I'm going to do this in my head and make sure that I check. 2x squared minus 14x plus x, which would be minus 13x minus 7. That looks good. That looks good. So we know that that's sometimes a little bit more difficult when this leading coefficient here is not 1. In this case, it's 2. Then we have to understand what that means in the factored form and how you're looking at factors of 2, vector pairs of 2, 2 and 1 is the option. Now we're looking at some domain issues too. X cannot be 7. X can also not be negative 1/2. If you attempt to plug either of those two numbers into f, it will implode and give you no result. It will give you an error. And it so happens as well that we have a factoring here, a division to do. So what we're looking at is that this initial f simplifies to this, where we want to maintain an understanding of equivalency and how it needs to maintain all aspects of the original f, including its domain issues. So that's a good day's work. Hopefully this was helpful for our algebra group. I'll see you next week. And if you're in stats, I'll see you tomorrow.